Today we will talk about forces, basically dynamics. As you know, first of all, let me repeat some physical quantities or some information so we could continue. Force, as you know, is a physical quantity, a vector quantity. It has a direction. That's why it might be sometimes challenging, complex, or interesting. So, till this point, you should revise vectors because very important. Here we will be working more than two forces usually, and addition of some forces, and the force is vector, and that's why vector addition will be very useful for our lesson. And here we use Newton's laws, as you know, three laws: first law, second law, third law. But today I will be talking only about second law, because first law and the third law, it's not very complex. Let me explain first law. As you know, if something, let's say we have an object and it's at rest, if total force equal to zero, forces acting on this object, resultant force equal to zero, it will be at rest. It will not move. So basically, this is the explanation of the first law. Or let's say you have an object, it's moving with constant velocity, and suddenly you apply 10 forces, but resultant force again equal to zero. It means this object will keep moving with the same velocity. It will not change its direction. So this is basically first law. Second law, again, simple equation. We have formula F equal to ma. This F is a vector, resultant force, and acceleration also in vector form. Resultant force equal to ma. This is the second law, and this equation is very important. We will explain this equation. We will learn how to apply, how to use this equation during our lesson. Third law, as you know, it's about action-reaction. If we apply, let's say, 10 Newton to the wall, same force in opposite direction will be applied to you. Shortly, we call it action-reaction. But here I will explain only second law. And when we will be explaining second law, sometimes we will use by default first law and the third law. So now let's come to this equation, F equal to ma. Again, F is the resultant force, so it's a vector. In order to make problem solving simple, we introduce free body diagram. Maybe you heard about it, free body diagram. So what is this free body diagram? This is a picture, this is a figure of an object or of the problem with all forces drawn on the notebook or on the screen. It doesn't matter. Basically, this is a picture of the all forces with its correct directions. Why it's important? Again, because of the vector. So, for example, let me apply free body diagram to an object which is located on the inclined plane, for example. We should draw all forces acting on this object, and when we draw it, it becomes free body diagram. So at the moment, for example, there is a weight mg, reaction force perpendicular to the surface, and maybe friction force, upward friction force. So these red lines that you see here, red arrows, free body diagram. This is a free body diagram, that's all. When you draw free body diagram, it will be easy for us to solve or to apply Newton's second law. Now, that's all. Basically, we finished forces, dynamics. Now it's a matter of solving problems. So let me start with simple problems and let's continue. So first example, simple example, let's consider an object in the air and it's falling downward. Of course, it will fall downward due to the gravity. Question, let's study its motion. So, now let's draw a free body diagram. Basically, how many forces acting on this object? We have only weight downward, mg. There is no any other forces. At this moment, we are ignoring the friction force of the air. No friction force. How this object will move? What kind of motion? Now let's come to the F equal to ma. This is Newton's second law. Here resultant force equal to mg, because only one force we have. That's why automatically it will be equal to ma, and acceleration of this object will be equal to gravity. So basically this object will fall downward with constant acceleration because gravity is constant, and this is a proof. So this is a motion of an object in the air when we ignore the friction force. Now let's consider the same object or another object moving in horizontal plane. So let me draw horizontal surface, again frictionless for now. We have an object. Let's apply force to the right. Let's call it F1. Now let's come to the free body diagram. Downward we have mg. There is a contact between this object and surface. It means there is a contact force or reaction force. Upward, let's call it m. That's all, no friction force. Now let's apply F equal to ma. So as you see from this free body diagram, from this picture, from this figure, we have forces in horizontal direction. Also we have forces in vertical directions. So we can apply this force, we can apply in both directions. So resultant force in x direction equal to mass times acceleration in x direction. Also resultant force in vertical direction, y, equal to mass times acceleration in vertical direction. So this is our axis, x-axis and the y-axis standard. So we have F equal to ma. I will try to apply it in horizontal direction and the vertical direction. In horizontal direction, this should be resultant force in x direction and the resultant force in y direction. So now let's start with horizontal direction. How many forces we have in horizontal direction? Only one I can see from the picture. So resultant force equal to F1 in horizontal direction, equal to max. So from here we can calculate acceleration in horizontal direction. Very simple. Now let's come to the F equal to ma in vertical direction. In vertical direction we have two forces, reaction force upward and the weight downward. So resultant force will be equal to reaction force minus weight should be equal to m mass times acceleration in vertical direction. And we know that from our real life, when we pull or push something in horizontal direction, it will move, it can move only in horizontal direction. It cannot fly upward, it cannot move upward, it cannot go inside the surface. So it will not move in vertical direction basically. Velocity in vertical direction equal to 0. It means acceleration in vertical direction equal to 0. So we can say ay equal to 0. So reaction force minus mg equal to 0. From here, for this specific problem, reaction force equal to mg. So let's continue with this next problem. Let's locate an object on the inclined plane and no friction force for now, and let's study. First of all, free body diagram, as we said before, very important. So downward we have a weight and the reaction force perpendicular to the surface. That's all. I can see only two forces here. Now we know that this object can move only by the surface of the parallel to the surface. Basically, it can move. There is only one way. It can move downward parallel to the surface. This is the direction of the acceleration. So let me choose my axis in this way: x-axis and the y-axis. So basically, resultant force in x direction equal to max, resultant force in y direction equal to may. Now, how many forces we have in x direction, in this direction? We have a component of the weight, because as you see, weight is not exactly in x direction, not exactly in y direction, so it has a components in x and y. So this part is mass geometry. This angle also equal to alpha, which is y direction, and the x direction will be equal to mg sine alpha, and the y direction will be equal to mg cosine alpha. So basically I can redraw these forces. In this direction we have a reaction force. In this direction we have a mg sine alpha. Opposite to the reaction force we have mg cosine alpha. This is a free body diagram, x direction and the y direction. So we have only one force in x direction, which is mg sine alpha, equal to max. So as you see, ax, acceleration in x direction, equal to gravity times sine alpha. Let's come to the resultant force in vertical direction. Here we have two forces, reaction force and mg cosine, opposite. So reaction force minus mg cosine alpha should be equal to mass times acceleration in that direction. Again, same logic. It cannot enter the surface. It cannot fly into the air. So again, acceleration in y direction equal to 0. From here, and reaction force equal to mg cosine alpha. Ax. Another example. Now let's consider more than one object. We have a horizontal surface, frictionless, no friction. We have two objects as shown in this figure, and let's apply F to the right. This is a M1, this is a M2. Let's find acceleration and the tension in the rope. So here we have two objects, so it means we should apply Newton's second law for both objects separately. And we have to draw free body diagram for each object. Now let me start with object number 1. So this is a first object, M1. Free body diagram. How many forces acting on this object? F to the right. There is a rope which is trying to stop this object. So to the left we have a tension. We call it tension, basically force in the rope. Downward we have its weight, and upward we have its reaction force. Let me call it N1 because we have two objects. And we know that it can move only in horizontal direction. It cannot again fly upward or enter the surface. It's impossible. So Fx equal to max, Fy equal to may. This is x direction, this is the y direction. Let me apply this Newton's second law for the first object only. Horizontal force, resultant force, F minus tension. To the right we have a force that someone is applying, and there is a tension force which is trying to stop this object, which is trying to slow down the motion, equal to M1, because we are considering the first object, acceleration of this object. Further, let me call it just A, because it can move only in horizontal direction, so we have only one acceleration. That's why let me call it just A. because there is no AY. In vertical direction, we have N1, downward we have M1G equal to 0 because of acceleration. So N1 equal to M1G. Now, let's come to the second object, M2. Free body diagram. How many forces acting? The same tension force, this one, is trying to move the second object. The same force is trying to stop the motion of the first object, but the same rope, same force is trying to move the second object to the right. Downward we have a weight, upward we have its own reaction force. So let me apply same equations in both directions. So resultant force in x direction, only T we have, equal to its own mass and acceleration. Acceleration for both objects will be same because of the rope. If you shift the first object for 1 meter, second object also will shift to the 1 meter. It means at any time they have the same velocity and the same acceleration. And in vertical direction, N2 minus M2G equal to M2 times acceleration in vertical direction, which is again equal to 0 logically. So reaction force equal to its own weight. So we have this kind of 4 main formulas equations. So let me substitute this equation, tension, into the first equation. So force minus M2A equal to M1A. From here, force equal to M1A plus M2A. From here, acceleration equal to force divided by M1 plus M2. This is acceleration. And in order to find tension, let me use this equation. As you see, tension equal to M2 times acceleration, which is force divided by M1 plus M2. So this will be tension in the rope. Now let me explain friction force. What is a friction force? Because till this point I explained it. I solved some problems without friction force by ignoring friction force. But not always we can ignore friction force. That's why first of all let me explain friction force. Then I will try to solve problems with friction force. So friction force basically force that tries to stop the objects. For example, from our real life we know that in order to move something, let's say we have a box and you apply force to the right, it will not immediately move. It will not immediately move. You need to increase force, and when force that you applied reach some certain value, only in that case it starts to move. So why? The reason is friction force. There is a contact between this box and the surface. It means there is a friction force between these two objects. And of course direction will be to the left in this case, because it tries to stop the object. So now how we can explain this friction force? If we can zoom this part, if we can zoom it, let me zoom it. The surface actually, it's not smooth. It has different levels. Surface is not smooth. So basically here we have so many forces. So it's not ice basically. When you walk on ice, it's difficult to walk because of friction. Friction is very small because the surface is almost smooth. But in real life, for example, you have a wood and wood. If two wooden blocks in touch, the surface of the wood is not smooth. That's why there will be some forces, and we call it this force in general friction force. Friction force reaches its maximum value when object starts to slide. Basically, when velocity becomes more than zero, when object starts to move, slide, friction force, it means friction force reached its maximum value. And this maximum value can be calculated by using this equation. Coefficient of friction times reaction force. We know what is a reaction force. Contact force between object and the surface. Coefficient of friction force, basically this coefficient explains the type of the material or how it's smooth, the ratio of smooth, etc. Basically it will be given in problems. For example, coefficient of friction force between wood and wood, between iron and wood, between plastic and plastic, etc. This is a small coefficient. This coefficient you need to multiply by reaction force, and this will give you maximum possible friction force. And this maximum value, it will reach to this maximum value when object starts to move. Only in that case you can use this equation. If object is at rest, it means friction force did not reach this maximum value. So, example. Again, same object, same box. We have a friction force, and let's apply some force. This force becomes, when this force equal to 0, this is a friction force, this force. Let me draw some table. When force equal to 0, friction force also equal to 0, because it will not move. Let me increase this force that we apply to this object. Let me increase to 1 Newton. Friction force also becomes 1, but it's still stationary, it's not moving. Let me increase to 2. Friction force also increases, becomes 2. But this object still at rest, it's not moving. Let it be 3. Still at rest. No velocity, no acceleration. Let's say the maximum possible friction force for this surface, for this object equal to 3 newtons. It means when friction force, when the force becomes more than 3, it will start its motion, it will move. So for example, 3.0001, friction force still 3 because it's a maximum value. Only at this case, our object will start its motion. Velocity will be equal to more than 0. When force becomes 4, friction force still 3. When force that we apply becomes 10, friction force still 3. Because 3 is a maximum value for this specific problem, for example. So this friction force equal to coefficient times reaction force, and it's equal to 3, for example. So this is how it works, basically. Now let's solve some problems related to the friction force. Friction force. Example. We have this kind of table. Here we have a pulley which can rotate freely. Here we have a M2, let's call it, and by the rope it's attached to the M1. Let's say here we have a friction force and the coefficient equal to mu. And the mass of this object M2 equal to, let's say, 10 kilograms. 10 kilograms. Question: what should be mass M1 so M2 could move to the right? It can only move to the right in this case. But this M2 should be enough to overcome the friction force between M2 and the surface. So let's find minimum mass that is needed to move the M2, for example. Okay, let's go. We have two objects. We need to apply Newton's second law for both objects. Before applying, we need to draw free body diagram for both objects. Let me start with M1. Downward we have a weight, upward we have a tension. So it can only move in vertical direction, logically. So resultant force equal to M1G minus tension equal to M1A. Minimum, its acceleration should be equal to 0. Minimum. M1G equal to tension. In this case, this object M1 will be at rest. Now let's come to the second object. To the right we have a tension, to the left we have a friction force, downward we have a M2G, upward we have a reaction force N2. And in horizontal direction, resultant force equal to tension minus friction force equal to M2A. And logically, this second object will move to the right if tension is greater than friction force, or at least it should be equal to the friction force, at least. And we know that in order to move this object, which we assume that it's moving, it means friction force reached its maximum value. So it means tension should be equal at least or greater than maximum value of this friction force, which is coefficient of friction force times multiplied by reaction force. And this reaction force equal to M2G for this problem, because upward we have reaction force, downward we have a weight, and again it cannot move upward, downward, so reaction force equal to weight. And this tension equal to M1G. So M1G equal or greater than mu M2G. We can cancel gravity. So mass M1 should be at equal or greater than coefficient of friction force times M2. For example, coefficient of friction force, let's say equal to 0.1. So M1 should be at least equal to 0.1 times 10. M1 should be greater than 1 kilogram. Only in this case, system can move. It should be greater than 1 kilogram. One more example, similar to the previous one, but in this case we have inclined plane, 30 degree. Here we have a smooth pulley. Here we have a M1. Here we have a M2 connected with a massless rope. Here we have a coefficient of friction force equal to 0.1 again. M2 equal to 10 kilogram again. Question. Find mass M1 so this system could rest. What should be mass M1 so this object, this system could be at rest, so no motion. Now let's solve this problem. So in this case, let me consider when friction force is directed to the downward and it almost reached its maximum value, but it's still stationary. So I will consider this moment. Downward we have a M1G and upward we have a tension. It's at rest. M1G equal to tension, it means. Now let's come to the object M2. Upward we have a tension. This tension should be equal to or greater, at least equal to friction force. And this is the moment that it's almost starting its motion. So it means it reached its maximum value. And in this case, reaction force equal to mg cosine alpha. downward we have a mg, perpendicular to the surface reaction force, let's call it n2. So as we explained it before, the opposite component to the reaction force equal to mg cosine alpha. So this tension equal to m1g equal to, this is m2 g cosine alpha. And there is one force we forgot to mention, so it's my mistake. I didn't draw free body diagram properly. So here downward we have a m2g sine alpha. As you see, if you don't apply free body diagram, there is a chance that you will do some mistakes. So here we need to add m2g sine alpha. So be careful. Always try to apply free body diagram. So we can cancel gravity. So m1 equal to mu m2 cosine alpha plus m2 sine alpha. Or we can take m2 here, so mu cosine alpha plus sine alpha. This is a one possible answer. So let's input data. 10 kilogram, 0.1 cosine 30 plus sine 30, m1 equal to, so it's time to use our calculator. Cosine 30 times 0.1 plus sine 30 . 5.8 kilograms. Now this is a limit of the mass when it will start moving downward. Now when we have a smaller mass, it will start its motion upward. There is a chance, so we will consider this moment. In this case we have a friction force upward. Downward we have a m2g sine alpha, and also we have a tension. In this case m2g sine alpha minus tension minus friction force should be greater than 0. Or we can say m2g sine alpha should be greater than tension plus friction force. Only in this case it will move downward. So tension again at least should be equal to m1g. So m2g sine alpha equal to m1g plus mu m2g cosine alpha. From here m1 equal to mu cosine alpha, m2 sine alpha minus mu cosine alpha, and this will be equal to, so 4.1 kilogram approximately. So we have two ranges. Maximum it can be equal to 5.8, minimum it can be equal to 4.1. So any mass between these two values will be, this system will be at rest. If you have a mass greater than 5.8, it will move downward, m1 will move downward. If you have a mass less than 4.1, this m1 will go upward, it will move upward.